Let's think of clocks. An hour and a half could be written as 1:30 or 1.5. We're familiar with both, so we know that they are equal, even though one is expressed in the clock system and the other in the decimal system. However, what if I told you what is 710 decimal in binary? In this lesson, we're going to learn how to convert numbers from a number system to another. Before we jump into conversion methods, let's take a look at how numbers are formed. For example, the number 333 in the decimal system. There is a reason why we call it 333. And that is, it is basically 3 hundreds and 3 tens and 3 ones. 300s and 3 tens and 3 ones in math look like 3 times 100 plus 3 times 10 plus 3 times 1. And that equals 3 times 10 to the second plus 3 times 10 to the first plus 3 times 10 to the power 0. And that is the original form of it. Those tens are called the positional multipliers. A positional multiplier is basically the radix of the number to the power of the index of the digit. Here we have the indices based on the position of the digit, and up there we have the positional multipliers. Note that this positional multiplier is powered to 0 because it's associated with digit 0. And this one is powered to the first because it's associated with digit 1, and so on. But what do we use these for, right? Why are we talking about positional multipliers and indices? We use that for something that is called positional value. A positional value of a digit gives you the weight of the digit, and it equals the digit times the positional multiplier for it. And that equals the digit times r to the power I. For example, we have 3 times 10 to the power 0, which equals 3. Or we have 3 times 10 to the first to express the weight of digit 1. But what if we add the fractional part to our number? 0.33 in decimal, for example. Does that actually change things? If so, how does that change things? Let's clear things up to see how that works out. 0.33, and it actually does not change anything. The indices will keep decreasing to the right direction. So we have d minus 1 with the position multiplier 10 to the power minus 1. And for this one, it's d minus 2, position multiplier to the power minus 2. And remember, 10 to the power minus 2 equals 1 divided by 10 to the second. Let's stop for a few new terms here. So this 3 here, it's the least in the whole number. We call it the least significant bit, or LSB for short. And for this one, which has the highest value in the whole number, we call it the most significant bit, or MSB for short. And we call this point the radix point. Note that to the left of the radix point, we start with 0. To the right, we go to the negative side. And that applies to all numbers in all number systems. Let's summarize what we've learned so far. Each digit in any number has an index, which is the order of that digit in the number, a positional multiplier, which equals the radix of the number to the power of the index, and a positional value, which equals the positional multiplier multiplied by the digit itself. So for this number that we have on here, d minus 2 has the lowest positional multiplier and hence is called the LSB, and d2 on the other hand has the highest positional multiplier and hence is the MSB, or the most significant bit. And the point here, which separates the whole part from the fractional part, is called the radix point. I know this seems like a math lesson more than a digital logic lesson. However, the digital logic course is like a building. The digital circuits and gates are the bricks. And the first chapter, which talks more about mathematical principles, is the glue that keeps them together. I would like to remind you to pause the video and take a breather at any time you feel like you are overloaded with information. Now we know the basics, let's see how converting a number from a system to another works. There are four main types of convergence. A. Conversion to decimal. B. Conversion from decimal. C. Conversion between binary and octal and hexadecimal. And D. Conversion between numbers in other systems. We'll start with the first type, which is conversion to decimal, meaning converting any number from any system to the decimal number system. Which is easier for you to communicate? 101101 in binary or 45 in decimal? Definitely the 45 in decimal, but as we know, an output of a logic circuit is more likely to be 101101 in binary, which is an equivalent to 45 in decimal. But how did we know that 101101 is equivalent to 45 in decimal? The rule says we get a decimal value of a number by basically finding its positional values and adding them up. In other words, by basically applying a summation formula to the positional values for the digits of a number. The formula is summation from I to n for di times r to the power I, where I is the index, n is the index of the highest positional multiplier, d is the digit, and r is the radix of the number we are converting from. I know you probably are not a fan of the summation formulas. I was not, but trust me, it is simple. Let's convert 101101 in binary to decimal using that formula. Let's clear things up, and the first step is to lay the number out in a neat way. So we have 101101, and then we assign the positional multipliers. Remember that we are converting from binary, so the radix here is 2. So we have 2 to the power 0, 2 to the first, 2 to the second, 2 to the third, 2 to the fourth, and 2 to the fifth. And now let's have the formula, our summation formula. We have the summation I to n for di times r to the power of I, and that equals the summation from 0, which is the index of LSB, to 5, which is the index of MSB. And then we have the digit times 2, because the base is 2, to the power I. And that equals d0 times 2 to the power 0, plus d1 times 2 to the first, plus d2 times 2 to the second, plus d3 times 2 to the third, plus d4 times 2 to the fourth, plus d5 times 2 to the fifth. And now let's plug the numbers in. That equals 1 times 1 plus 0 times 2 plus 1 times 4 plus 1 times 8 plus 0 times 16 plus 1 times 32, and that equals 45. So ladies and gentlemen, 101101 binary is 45 decimal. Let's see an example in that kind of conversion. Convert 10001.11 binary to the decimal system. Okay, we start with laying the digits out. So we have 10001.11. And then next we lay out the positional multipliers, and remember that the radix here is 2. So 2 to the power 0, no, not quite. We've got the radix point. The index here is not 0. The index here is minus 2. We have 2 to the power minus 2 here, and then 2 to the power minus 1, 2 to the power of 0, because the index 0, 2 to the first, 2 to the second, 2 to the third, and 2 to the fourth. Those positional multipliers will always have the same values. So instead of having them all cluttered up here with their powers, let's put their values in. So we have 1, 2, 4, 8, 16. On the other side here we have 1 over 2 and 1 over 4. Now we have both the positional multipliers and the digits laid out. Let's find out the positional values so we can convert the number. And we're not going to strictly stick to the formula. We're going to do it in a more appealing way. So we lay out the multiplication here to find the positional values, and the plus signs here to sum the positional values up, and then all in one equation that looks like 16 plus 0 plus 0 plus 0 plus 1 plus half and plus quarter. And that equals 17.75 in decimal. So we have converted the number successfully. But there's a thing that we have to point out here. So in binary, it's always either 1 or 0. And let's see how that affected our equation. So when the digit was 1, we only got the positional multiplier, as in 16, 1, 1 over 2, and 1 over 4. However, when the digit was 0, the whole positional value was 0. So we can just cancel the whole term, as in 8, 4, 2 here. So let's see how this affects our approach. This mostly helps us with shortcuts. So let's lay the digits down again. So we have 1, 0, 0, 0, 1.11, and the position multipliers. So we have 1 over 4, 1 over 2, 1, 2, 4, 8, and 16. And then we have 1 here, so we get the position multiplier, which is 16. The next digit is 0, so we skip the whole term. And the same applies for the next two terms because the digits are zeros. And the next one is 1, so we get the positional value. So we got 16 plus 1. And the same applies for the rest because they are ones. So we've got 1 plus 1 over 2 plus 1 over 4. Sum that up and we will get 17.75 in decimal, the same result. And this applies to all systems, by the way, whenever there is a 1 or a 0, but it's quite beneficial here because the binary system consists of zeros and ones. Speaking of other number systems, let's take an example on converting numbers from the octal and the hexadecimal systems to the decimal system. Our example says, find the decimal equivalent of the following: A, 751 in octal, B, AD2 in hexadecimal. The same principles apply, so you can pause the video and try to solve it on your own. Alright, let's start with the first number, 7, 5, 1, and then the positional multipliers, 8 to the power 0, 8 to the first, and 8 to the second. And then we get the positional values and sum them up, so we have 7 times 64 plus 5 times 8 plus 1 times 1, and that equals 489 in decimal. And now the second number, AD2 in hexadecimal. We lay the digits out, AD2, and then 16 to the power 0, 16 to the first, 16 to the second, and that equals A times 256 plus D times 16 plus 2 times 1. And remember that A is equivalent to 10 and D is equivalent to 13. So we have 10 times 256 plus 13 times 16 plus 2 times 1, and that equals 2,770 in decimal. I'll leave you extra numbers to convert to decimal. The first number is 11101.010 in binary. The second number is 32.2 in a system with a radix 5. And the third number is FF in hexadecimal or with a system with a radix 16. You'll be able to find the answers for these questions in the PDF attached to this video in the description.